So let's go over the next part of the note guide, which I believe is part 3 here, and it goes over Newton's second law and Newton's third law. So to start with, Newton's second law, I guess it's probably best to start on this slide down here, the third slide on this page, is written as F equals ma. So this is the way you're going to see it, the way you'll probably remember it. Even after I talk about it, this is probably what you'll remember. And if you ask most people what Newton's second law is, they'll say F equals ma. And maybe that's how you learned it back in middle school or elementary school or something along those lines. All right, so now let's go back up to the beginning here. It says Newton's second law, net force causes an object to accelerate. So one thing you've seen already in this class is that we like to write this as sigma. Let me see if I can zoom out a little bit. Sigma F, right, is equal to, and maybe it's written for one direction, sigma Fx equals max. So we like to write it like that. But understanding here that Newton's second law can be written as the sum of the forces. Or like that, and that sigma F is the net force. So this can be considered F net in the x direction or F net in the y direction. Okay, so when we say sigma F, we mean the same as F net. All right, and I can go ahead and fill that in. Net force can also be written as sigma F. And I just wanted to put that symbol on there in the note guide. One thing worth mentioning, I guess because we kind of filled out most of this third slide, is that the acceleration occurs in the direction of the force. Forces are vectors. Because the acceleration is a vector, the force is a vector, but they occur in the same direction. And for whatever reason, sometimes students forget that. I will ask them what direction is the acceleration in or what direction is the force in, and they are identical in direction. All right, let's go back to this first slide. So net force causes an object to accelerate. So that's kind of the idea that when you think of forces from now on, you should think of accelerations because they go together, right? And this is what Newton's second law is saying. Okay, so should we write that down? Forces go with accelerations. Or you could have said accelerations go with forces. All right, acceleration of an object is directly proportional to the force acting on it. Less force to accelerate. So this makes sense, right? If the force is large, the acceleration is large. Okay, so this kind of gets at an idea, though, that that knowing Newton's second law, F equals ma, is not quite the same as understanding it. So this is Newton's second law. But understanding Newton's second law is best thought of this way. So if you really want to understand it, rewrite it as A equals F over m. This is the same thing that we just wrote up above, except now it's in a different form, which allows you to understand what is happening. And what this shows is that if the acceleration, or if the force is large, right, then the acceleration is large. That these two are directly proportional. One goes up, the other goes up, and so on. And that's what we just wrote. But we can also see that the mass is I didn't really like that. I was looking for see if I can erase that. Let me grab a different color here, maybe blue. The mass is inversely proportional to the acceleration. Meaning as the mass is larger, right, then the acceleration is less. You can think of this if you were trying to push a book across a table, right? And you used all the force you had, right, to push this book. But then you replaced the book by something a lot heavier with a greater mass. And you once again used all the force you could, right? And of course that object with the greater mass wouldn't accelerate as much. And so we see an inverse relationship. As the mass gets larger, the acceleration is less. So it says up here, less force to accelerate a blank mass object than a... So it takes less force to accelerate a lower mass object than a greater mass object. I wouldn't worry too much about that. I'm filling in this note guide, which I wrote years ago, but worry more about what I'm saying right now. Newton's second law quantifies the relationship of force, mass, and acceleration. Okay, let's write this then. So what we're saying here is, if we think of Newton's second law as this, right, as this relationship, A equals F over m, what it's saying is the acceleration. I don't know if it's going to be enough room to write. Let me see. Is directly proportional to the force. So meaning larger forces give you larger accelerations. Should make sense. Okay. And the acceleration is directly proportional to the force, and the acceleration is inversely proportional to the mass. So we're saying with that second part, we are saying that a less massive object accelerates, or a more massive object accelerates less. Let me say it this way. The larger the mass of an object, for a constant force, right? The less acceleration it experiences. Okay. The larger the mass of the object for a constant force, the less acceleration it experiences. The smaller the mass of the object, the more acceleration it experiences. Okay, so they're opposite. All right, so up here it says in this next sentence, the acceleration of an object depends directly upon the net force acting upon the object, and inversely upon the mass of the object. Okay, hopefully that makes sense. And once again, to think about all of this, make sure you rewrite F equals ma, and you rewrite it as A equals F over M. This is the way to make sense of it. This is the way to understand. Now you can see the direct relationship between A and F, or the inverse relationship between A, whoops, I was looking for A, that A and M. All right. Good. I think that's about it right there. Let's go ahead and, I guess that's about all I want to say about Newton's second law. Hopefully that's making more sense. And you realize it's more than F equals ma, and it's going to show up in tougher problems as sigma fx equals max and sigma fy equals may. But once again, the rewriting as A equals F over M. Okay, let's move down here to Newton's third law. Okay, so Newton's third law. Newton's third law starts off by stating that single isolated forces cannot exist. Let me just write that down right under here. Let me write it a little differently. In the universe, all forces occur in pairs. So that's interesting to think about. So every force that happens has an equal and opposite force in the universe. All right, so we're saying that single isolated forces cannot exist. Forces must exist in an action-reaction pair. Newton's third law states, I think a lot of times students have heard of this one. Let's go ahead and write it out. For every action, comma, there is an equal and opposite reaction. For every action, there's an equal and opposite reaction. All right. Now, even though this is probably one of the easier ones for students to remember, it is also one of the harder ones, probably the hardest one to understand and to apply correctly. Let's kind of talk about why. So another way Newton's third law can be stated is the force of object 1, forgot the force of object 1 on 2 is equal and opposite to the force of object 2 on 1. All right. So if we go back to the definition of for every action there's an equal and opposite reaction, something we have to understand about Newton's third law is that the action-reaction happens at exactly the same time. And that's tricky because a lot of times when people think Newton's third law, they think something like this. They're like, for every action, there's an equal and opposite reaction, right? This first definition. Hold on a second. Let me highlight this. All right. They think something like this, and then they use an example like this. Say, for instance, you have like a annoying little brother or something, and he starts annoying you by putting his hand like near your face, and so what do? You swat his hand out of the way. You're like, what are you doing? Get your hand out of my face, and so you're like, okay, so the action was your little brother trying to bother you, and your reaction was you pushing his hand away, right? But that's not what Newton's third law is saying, right? Newton's third law is saying that the two things happen simultaneously, not one then the other, right? And so that is a difference, that the action reaction happens exactly at the same time, simultaneously. Okay. So, and this is kind of crazy to think about then. So then, therefore, either force could be termed the action or reaction. All right, because they happen at the same time. Interesting. Okay, let's go ahead and move to the next slide. Okay, so if equal and opposite forces balance, then how is motion possible? All right, before we get that one, let me just write this down. What I'm doing here is I'm kind of gathering up some ideas of why Newton's third law is more than just for every action there's an equal and opposite reaction. And so far I've gathered up two parts of Newton's third law that are not directly stated, right? And for every action there's an equal and opposite reaction. Okay, let's go look at this next slide. Newton's third law. If equal and opposite forces balance, then how is motion possible? So what this is saying is, well, if I was to say throw a ball, right? If there's an equal and opposite force for me throwing the ball, then how does the ball move forward? Right? And I always ask students this, and they're like, or they start to think this, and they're like, if there's equal and opposite reactions, don't they always balance out? And what you have to remember for a person throwing a ball, I don't know if I can draw this very well. Looks like he's holding a pizza or something. All right, the person's going to throw a ball, that when the person launches the ball, oh man, let's see if I can fix that. Let's see. When they throw the ball, that the person puts a force on the ball. F person on the ball. I'll just write comma ball, person comma ball. Or maybe I should write on, just to keep it as clear as possible. That there's also a force from the ball on the person. And this is the Newton's third law pair. So what I'm trying to say, the reason motion is possible is that these equal and opposite forces must occur on different objects. Seems obvious enough, but like I said, it confuses students. So let's write that down as the third part. Force pairs, maybe. Must. It's very important. All right. So once again, that's not directly stated in for every action there's an equal and opposite reaction, right? So we have three different parts of this law that that aren't quite stated in for every for every action there's an equal and opposite reaction. And maybe we can say, instead of all forces occur in pairs, maybe we can say, well, I guess if I was going to get all the parts of this, if I had a part 0, maybe force pairs are equal and opposite. Like I said, I'm just trying to gather up everything about this law here. Okay. Anyways, Newton's third law. Draw a free body diagram of a nail that has been hit into a piece of wood by a hammer. Why does the nail accelerate? And this kind of gets at the idea of equal and opposite forces like we just did. And so if I draw this, so here's the nail, and it's being hit into a block of wood. And what we can see, well, let me finish drawing this. Here's a hammer. Obviously, this isn't drawn, to scale or anything. We can see that we have a free body diagram, say, for the nail. And we have maybe force normal. I guess maybe friction pointing up too, right? Because the object's going to move this way. So maybe force friction if you want to add that in. But then you have the largest force, right? Which is going to be the force of well, then you have Fg, obviously. Maybe not obviously. Once again, that's also very small because it's a nail. But you have the force of the hammer, the force of the hit, right? So you have force of the hammer on the nail. And maybe I'll make this one purple. And my point here is that equal and opposite force of that is also purple is occurring on the hammer. Assuming this hammer hits, dead on with this nail. So this would be the force of the nail on the hammer. Whoops. Hammer is a hard word to spell. All right. So why does the nail accelerate? Well, if we look at the nail, right, and we look at these forces that are occurring here, we can see there is a net force directed downwards. Right? And you can also say, well, if there's a net force directed downwards, there's got to be an a net acceleration directed downwards, right? Because F net equals m, the mass of the nail, times a net. Right? And here you have the Newton's second law written with net force and net acceleration. Okay. All right. The action-reaction forces are equal and opposite, but once again, they occur on different objects. Running out of room. Got room here. All right, so hopefully this is making a lot of sense. And Newton's third law of pairs, once again, quick review of how these forces occur and what Newton's third law is saying. What students and most people remember, for every action there's an equal and opposite reaction, right? That's what most people are going to remember. But correctly stated or correctly thought about, force pairs are equal and opposite. All forces occur in pairs. So let me see if I can do a little highlighting here. Equal and opposite. Forces occur in pairs. Happen at the same time. And must occur on different objects. I'll highlight must too. All right. So there you go. That's kind of Newton's third law there. And picking these force pairs out is not easy. Let's go... For instance, if we thought about this one a little bit harder, Let's see. We'll make force normal. We'll go with brown. If force normal is this brown force right here, right? Force normal is the force that the block pushes on the nail. So there's a force normal down here of the nail pushing on the block. There's the equal and opposite force normal. Friction also would have to have a equal and opposite frictional force on the block, right? And that's tricky too. But let's go ahead and draw that. Let me see here. So if I drew a dot for the block, and let's make friction maybe green. So we are saying there's an equal and opposite frictional force on the block. All right, tricky. And then finally, where is the Newton's third law of pair for force gravity? This one's probably the toughest one. We'll make it pink. Is pink going to stand out? I don't know if it's going to. All right, kind of looks pink. Still looks red on my screen. All right, that looks pink. All right, so what we're saying is the Earth pulls the nail downwards with force gravity. So therefore, and this one's kind of crazy, but it's true, the nail pulls the Earth. The nail pulls the Earth upwards. And that's on the Earth. So if I drew the blue dot right here, this is the Earth down here. All right, so there you go. All four forces with a force normal pair, a Newton's third law pair. We have force normal, force friction, force gravity, all with their third law pairs. And finally, force hammer on the nail, the purple vector having its third law pair on the hammer. Okay, so now you can see why this gets tricky for students to find, and so on. Yeah, friction one I didn't really explain that much, but it's a resistive force for the nail to move into the block. You can think of it as a resistive force for the block to move against the nail. So yeah, because the two have to pass each other, right? As the block goes into the nail or the nail goes into the block. Yeah, that's kind of what we're saying, that there's a resistive force between the materials. All right, we'll talk about friction in the next video more. Okay, hopefully this is making sense. And yeah, once again, these 4 points. So that's it. Have a good day.